Okay, well, happy, that's actually Wednesday. Oh, I didn't get the wrong date there. It's week 4 now. It's Wednesday. I know you guys are asking about homework 3, and I apologize. I haven't gotten it ready. But, whatever homework I post, I'll make sure you guys have, enough time to complete it. I guess before we go on, I want to just kind of get a pulse from the classroom and get and then depending on what your initial reaction is, we'll I might turn this into a formal poll. Right now, for the grade breakdown, I've got 25% for the final exam. That's scheduled for week 6 Friday, last day of class. And I'm wondering if you would prefer to have a second Kaggle competition for a classification problem. So right now on Kaggle, you have a regression problem where you're trying to predict the percentage that voted a certain way. And I'm wondering, kind of a similar, right now it's 20 and 6. It would probably be a 20 and a 5, and make a second group project where you would do a classification problem rather than, and then there would just be no final exam, and you would be and you would just have kind of a second thing. So
2 separate papers, right?
Yeah, 2 separate papers, 2 separate things. I suppose if you wanted to ditch your group, I could allow for that or something, for the second project or something.
For the
but
paper, like the details on it.
I haven't published. I know I'm like super behind. I'm like, I've been trying to redo a lot of this stuff to incorporate tidy models, and I apologize. That is on my things that I need to do, which is publish the grading rubric for the paper, how that's going to work, create a homework 3, and update some other stuff. But okay, just kind of initial feelings, and you don't have to make a decision now, but does that sound appealing, or do you feel like let's just potentially, right? Okay.
It depends, I guess, how much of a time investment the paper itself.
Depends how long, so
that's a factor.
Okay, all right. Well, I guess I'll have to publish the grade rubric, and I'll let you decide. Okay, so
When are we gonna?
I'll probably
This week.
I would probably need to have the vote completed by Monday of next week, and then that way I can make sure you have enough time for the second project if you want, if that's what the class decides. Okay, and we'll just whatever the vote is, it'll be a majority wins type of thing. Okay, well, I guess we'll see what how that goes. All right. So let's take a look at today's lecture, and we are going to be working through Chapter 6 of our textbook, Linear Model Selection and Regularization. And we touched upon some of these ideas already, but in particular we'll look at subset selection and shrinkage methods, and there's also another book that you can read called Feature Engineering and Selection, and that's available here again to read on as you might want on your own time. But there's some good stuff in here. Okay. But feature selection is chapter 10 in this book, and so that's That's a spot you can turn to and read. And the idea here is, how do we, how can we select what our linear model should look like? So, you know, if you fit some kind of linear model, how should we select our coefficients, and should we select a subset? Okay. And so, you know, the linear model is basically some combination of X predictors along with coefficients. And these coefficients, beta 0 through beta p, if you have p predictors, you know, we estimate these things by trying to reduce the total squared residuals. Okay. And so, what we might want to do is we might want to change the way we select these coefficients. Okay, and so so least squares regression will give unbiased estimates with the least amount of variance if the variables are uncorrelated. So, you know, they're known as your best linear unbiased estimators, your BLUE. But we can try a different method for figuring out these coefficients, and if you do that, you might actually improve your prediction accuracy or your model interpretability, you know, perhaps at the expense of now having biased estimators. Okay. Okay, and so how does this work in terms of improving prediction accuracy? Okay, well, if the number of observations you have is a lot bigger than the number of predictors you have, so if you have like thousands of observations and only, you know, 5 predictors or something like that, least squares regression works pretty good. Okay. But on the other hand, if your n is not bigger than p, okay, not that much bigger than p, then there can be a lot of variance in the least squares fit. So depending on what random sample you get, your estimators for your slopes and your beta coefficients can vary quite a bit from one random sample to another. And you can end up overfitting your data, or you can just have poor predictions. Okay. And in fact, sometimes this happens where the number of predictors is greater than n, and in that case, least squares regression will fail because you'll have there's not a unique set of coefficients. Okay, and you'll in fact have infinite variance as far as the estimates go, right? And so the way we can deal with this is we can constrain or shrink, and we'll look at some shrinkage methods for the estimated coefficients. And when you do this, this reduces the variance of our estimates, variance of our coefficient estimates, but it comes at the cost of introducing bias. And depending on the situation, it's going to be worth it, and in other cases it won't be. Okay. Interpretability often improves if fewer variables are used, and we can remove some of the variables by subsetting. We can also remove variables by just setting their coefficients equal to 0. When you do least squares regression is unlikely to push any of the coefficients to exactly 0, and so, you know, when we do look at some shrinkage methods, we'll achieve this by pushing some coefficients to 0. Okay. So here's a few ways we can modify the way we do select our linear model. As one is subset selection, and you kind of had to do a little bit of this in your second homework, and I know students had questions on exactly what's the best approach for this. Okay, And then we can also take a look at shrinkage methods. There's also dimension reduction methods, and so we'll talk about all of these things. Okay. So one method is subset selection. So if you have a bunch of predictors, you might say, okay, let's say you have 10 predictors, and you want to figure out what is the best subset of models to, or a subset of variables to use, okay? And one is best subset selection. Best subset selection is computationally very expensive because it requires you effectively to fit 2 to the p different models, and you're going to find the model with the best subset, okay? And so so if p is very big, then this becomes very, very impractical, okay? But effectively, you start off with the null model. The null model has no predictors, and you would predict the mean for all observations. And and this forms a baseline for your RSS, okay? Because your RSS is basically the total sum of squares from the mean, okay? So basically the numerator of the variance. So if you think about the variance as total sum of squares from the mean divided by n minus 1, it's basically the variance times n minus 1. That's going to be kind of your baseline RSS. And then you're going to fit a whole bunch of different models. So first you're going to set k equal to 1, and you will fit all the models with just one predictor, okay? And among those k different models, you will pick the one that has the highest r squared value, okay? And then you'll look at k equals 2, and you're going to have p choose 2 models that have k predictors, right? If you have 10 predictors, you'll have 10 choose 2, which I think is 45, either 45 or 55. 10 choose 2, okay? And what was I saying? Okay. And then you have to pick from among those with the largest r squared value, and you'll do this for 3 predictors, 4 predictors, 5, okay, until k reaches p. And then among all of those different models, you'll look at the model with no predictors, the model with 1 predictor, the model with 2 predictors, the model with 3 predictors, and so on and so forth. You would select the best model using some kind of cross-validation or some other kind of criterion. So that would be best subset selection. And again, with p different predictors, this could be very expensive, computationally expensive. Okay, it does reduce as far as comparing the models from 2 to the p. So you're going to have to fit 2 to the p different models to kind of reduce it down to these p plus 1 different models. But now you can just compare among these p plus 1 different models. So you'll have the best model with no predictors, the best model with 1 predictor, the best model with 2 predictors, up through the best model with all p predictors. So there's only one model here and one model here, but you've got a whole bunch of other models in between. And you compare those, and you want to decide which one's the best, okay? And then, when you compare the models between, should I go with the model with 2 predictors or 3 predictors or 4 predictors? We have a few different ways to evaluate this, right? We don't, in those cases, we don't want to use RSS because RSS always improves as you add more predictors, okay? So as you go up to p predictors, RSS or r squared is always going to get better. So we can use kind of alternative values like the AIC or BIC or adjusted r squared to kind of figure out which one's the best, and we can take a look at some of these things. Okay. For large values of p, fitting 2 to the p different models is not a good way to go. So we can try these kind of stepwise selection methods, forward stepwise and backward stepwise. Now, to be honest, these stepwise selection methods have kind of fallen out of favor, right? So I imagine these were covered in 101A, your forward and backward stepwise selection methods, and this is probably what you used in your homework too, just to kind of figure out, you know, for one of your homework problems. But I would say these models have fallen a bit out of favor, or these methods have fallen a bit out of favor. But the idea here is they're greedy in that they're going to pick the best model that performs at that time, which, you know, you're taking a step in this direction, but, you know, in the long run, it might not be it might not result in the best possible subset. Okay, so again, you start off with an empty model, and for forward stepwise selection, you're going to add one predictor. So starting off with 0, you're going to add one predictor, and what you have to do is you have to fit all P predictors one at a time. So you say, okay, well, what if I add variable 1? You know, how much of an improvement in R squared do I get? What if I add variable 2? How much of an improvement in R squared do I get? What if I add variable 3? How much of an improvement in R squared do I get? And you do that one at a time, and then and you find the one variable that, if you add it, will result in the greatest improvement in R squared. And then you take you say, okay, well, now I have one model locked in. What's the best that would get if I have 2 variables? Okay, and then so you would add one variable at a time. And so, you know, if you have P predictors, now you have P minus 1 predictors to try out. And you say, okay, so let's say in the first round you decide that I don't know, variable income is the most powerful predictor. Okay, so you're going to choose whatever income is. All right, so you lock in income, and then now you look at the other variables. All right, you look at variable 2, variable 3, variable 4, variable 5, and you look at income plus variable 2, income plus variable 3, income plus variable 4, and you compare all of these different models, and you say, all right, which of these models that include income plus one other model or one other variable has the best R squared value? All right, and then you do that. And then now that you have 2 variables locked in, then you try adding one variable at a time. Okay, and again, it's kind of a pain, but it could work. All right, and you're going to select the best model among. So you do this, and so basically, you know, M1 is a smaller model of M2, and M2 is a smaller model from M3, and so all of these other models are kind of contained in each other, and you can find the best using kind of cross-validation or some other criterion. I mean, at this point, because all of the models are basically smaller models of smaller versions are contained within the other models, you can also do the log likelihood test, okay, or likelihood ratio test, I should say, and you could see, you know, is it worth spending that extra degree of freedom to add this additional predictor and things like that. Okay, this again, it performs fairly well, but it's not guaranteed to find the best model, and again, it's kind of fallen out of favor. Same thing with backwards stepwise selection. Okay. And backwards, you start with all P predictors, and then you say, all right, which one of these can I throw out? Okay, which one of these can I throw out? And you just do it one at a time. I know a lot of students, when I was kind of talking to them in office hours, you might have started with the full model with P predictors, and then, you know, maybe like 4 of your predictors are not significant. So, you know, it's tempting to just kind of jump to the next thing or just drop all 4 of those insignificant predictors. But that's not backward step. That's just a little bit arbitrary, right? So, because every time you drop a predictor, it could kind of dramatically change some of the other things. Okay, it could in that, and that's one of the things with linear models is that the variance in your coefficients are high, and especially if you have high collinearity between certain variables. If you drop one variable, it could suddenly make some of the other variables a lot more significant and things like that. But again, backward stepwise selection. All of these involve fitting a ton of these different models. Let me give you your first view quiz answer. But I got to look up the values here, sorry. Okay, so your first, oh, that's not. Okay, your first view quiz answer for today is the letter B. It's the letter B. B as in bear is your first view quiz answer. B. B as in bear. B as in bear. Okay, so as far as the decision criterion, what do we use to decide how many predictors should we have? Should we have 2 predictors, 3 predictors, 4 variables, and things like that? And here are a couple values that we could use. You have Mallow's CP. Lower values are better. AIC, which is kind of it's very closely connected to Mallow's CP. The Akaike information criterion. Also, again, lower is better. And then you have the BIC Bayesian information criterion, lower is better, and then adjusted R squared. And there's formulas for each of these things in our textbook. Okay, and so this is the formula. It's RSS plus 2 times d sigma squared. Okay, basically a penalty for each of these kind of predictors that you add. Okay, so if you have d predictors, there's a penalty for each of those things. And AIC is basically there's some additional constants. Okay, so CP and AIC are proportional to each other. Okay, and then for the BIC, this quantity basically gets bigger as at a rate of log n. Okay, log n for however many observations you have, rather than d. So usually this is going to be a bigger number than 2, and so for each additional predictor, okay, as d goes up, your BIC climbs a little bit faster than your AIC. Okay, and so what this has, the effect that this has is we can look at kind of the same data set, and we could say, all right, how which one produced the smallest AIC, which one produced the smallest BIC, and things like that. And basically, we can say, all right, adding a third predictor, even a fourth predictor, reduced the these values. But then adding a fifth or sixth or seventh, we start to incur penalty, right? So as we add more predictors, it's actually, the BIC says it's not worth it, okay? And the CP says, it's not worth it adding going past 6. So between the two, between AIC and BIC, in general, BIC will prefer models with fewer predictors than AIC, all right? And then the adjusted R squared, in that case, larger values are better. And these are adjusted in terms of, R squared always climbs, gets bigger as you increase the number of predictors, and adjusted R squared basically includes a little bit of a, reduces the RSS by, divides by the number of predictors here, okay? So, so as the number of predictors gets bigger, the R residual sum of squares, the numerator in the adjusted RSS will shrink a little bit, okay? So again, these are just kind of ways to kind of compensate for the fact that you're adding more predictors. Because again, as we add more predictors, R squared goes up, RSS goes down. And it would always kind of favor the model with the most predictors. And to kind of compensate for that, we just say, you know what, there's a penalty for adding more predictors. And that's what we can do. So these are ways to do it. We can also use cross-validation. All right. So, and this is kind of probably the more machine learning approach, right? So, because over here, you'd be faced with a choice. Do I use AIC or BIC or the adjusted R squared as the way to choose the number of predictors? You can just use cross-validation, and you don't have to make a choice, and you can just say, all right, which of these models, the number of predictors to use, which one results in kind of the best cross-validation error, right? And so here we're hoping that the training set, our validation set, is representative of the test data. That there's at least similarity enough so that when we run cross-validation, whatever number we're getting is going to be pretty close. A good selection there. Okay, so this is so here we're looking at cross-validation error versus how does BIC compare versus just having one validation set, okay? And here BIC says go with 4 predictors, using one validation set, ends up picking 6, and then if we do cross-validation, we end up picking 6. But if you look at it, what's the difference between 4, 5, and 6? It's the difference between each of these things seems pretty small. Okay, so maybe it's not too dramatic, at least for this particular data set. Okay, and again, things vary from one data set to another. Okay, let's talk shrinkage methods. Okay, so with shrinkage methods, we adjust the function that we're trying to minimize. Okay, so with ordinary least squares, we say we're going to pick the beta coefficients that are going to minimize the residual sum of squares, right? So we really just want to minimize the difference between what we predicted and what that actual value is. Okay, and we're going to pick the betas that do that. With ridge regression, so the shrinkage methods are ridge regression and lasso. With ridge regression, we add this term over here, lambda times the sum of beta j squared. And we say this is the quantity, okay? This is the quantity that we want to minimize, right? So RSS is still part of the thing that we want to minimize, okay? But we're also trying to, we have to keep in mind that that the size of the betas themselves factor in to this quantity that I want to minimize, right? So, for example, let's say you're trying to save money, okay? You're trying to save money, and you can say, I want to minimize how much I spend on rent. All right, let's say you just want to minimize how much you spend on rent, okay? Okay, then you might end up living in, I don't know, Bakersfield or something, far away, because apartments there are super cheap, right? But if you go, okay, well, you know what? Minimizing rent only, okay, or actually, you know, minimizing rent, you might live in, I don't know, some other state, right, where the cost of living is way cheaper, okay? That's actually not a good thing, because the total cost of that situation will end up being a lot higher if you have to commute to campus and things like that, right? So we might say, okay, you know what we want to do is we want to minimize the total cost, which is going to include rent plus transportation costs, okay, plus transportation costs, all right? And so now you don't want to pick the apartment that's super cheap but super far away, because what happens if you go super far away, your transportation costs go higher, right? And you know, with gas prices very high, you know, the distance from campus, you know, and your commuting time, this might actually favor apartments that are closer to campus, okay? Versus, and so now you have kind of these two things at play that you want to minimize, right? So in general, apartments closer to campus will cost more, and so you know the rent cost, or in this case, you know, maybe the optimal choice isn't the one that's next door to campus, okay, but also the one that's optimal isn't the one that's a million miles away, okay, but something in between, right? And you know, there's probably other things that factor in, but if it's just kind of like a reduction in cost only, and you factor in, you know what's the cost of the gas and the transportation and all of that, okay? And so here you can say, you know, if gas was $50 a gallon, okay, then that would end up favoring apartments closer to campus, because you really want to avoid spending money on gas, right? Okay, and on the other hand, if gas was only $1 a gallon and you had unlimited time and you didn't really care about the hours it took to commute, you might end up living, you know, super far away, because, you know, the cost of the gas itself, not that big of a deal, okay? So anyway, it's kind of like that, except here we're trying to decide what are the best beta coefficients, okay? And so the best beta coefficients to reduce RSS will be one set. But let's say the one that minimizes RSS includes some beta terms that are big, okay? And when you square those things, they get even bigger, and so basically, when you do ridge regression, the coefficients that we end up choosing aren't going to be the same beta coefficients that minimize RSS, okay? Some of those values are going to be too large, and so instead we're going to settle on values that don't minimize RSS, but minimize the total sum of this thing, okay? So we're going to end up picking beta coefficients that aren't as good at minimizing RSS, but kind of minimize this, not minimize, but reduce the amount of penalty that we incur. This shrinkage penalty, where we're kind of take the beta coefficient, square it, and add them up, it applies to all of the predictors, all the predictor variables, but not the intercept, okay? And it's recommended that if you're going to do ridge regression, you should kind of standardize your predictors so they're all on a similar scale. Because if one of the variables, you know, as far as, say, salary, let's say income, you can report income as direct money in dollars, or you can report it as in thousands of dollars, right? So somebody can say, my income is $32,000, okay? Or you could record that as the number 32. And if you think about, all right, what is the coefficient for beta, okay? And let's say you want to predict how much someone can afford to pay for rent based on their income, okay? So if the number is 32,000, you know, every dollar you add allows you to afford basically another 5 cents in rent, right? But On the other hand, if you're recording income in thousands of dollars, so going from 32,000 to 32,001, how much more rent can you afford each month? Maybe that change is like 5 cents, okay? But on the other hand, if you go from 32,000, all right, and you're recording 32 and you add 1 and it goes from 32 to 33, so you're going from 32,000 to 33,000, how much more can you afford in rent each month? Okay, maybe now you can afford another $40 in rent or something like that, okay? So an increase of, so one, the coefficient would basically be 0.05, adding 5 cents, and then the other one would be adding, say, 40 or 50, basically 1,000 times as much, right? And so, so the coefficient is drastically affected by the size of the values themselves, okay? Are you recording values, in actual dollars going, changes in X go from 32,000 to $32,001, or are you recording things in thousands of dollars where a change in X goes from 32,000 to 33,000? That's going to dramatically affect the size of your coefficients, okay? And therefore, when you talk about minimizing your coefficients, someone could try to just cheat their way and just say, oh, you know what? I'm going to, multiply my X values by a constant or divide my X values by a constant. And so we would recommend standardizing your variables, okay, so that they all kind of are on a similar scale or have the same standard deviation. Yeah, question?
I'm still a bit confused. Like, what's the ultimate goal of doing the shrinkage method? Like, why bother?
Yeah, so I guess it depends on the situation here. But if you're in a situation here with let me get to this slide, and then maybe we'll answer this, okay? So here's just kind of a picture of how the coefficients will shrink as we increase the lambda. And notice this is on a log scale, okay? So it looks like, oh, we're just increasing lambda, but it goes from basically lambda being 10 to the negative 2 to 1 to 100 to 10,000, okay? And this is after we standardize the values, what are the coefficients, okay? And we have coefficients on income, limit, rating, and student, and things like that. And we can see these things, in general, as lambda increases, they shrink down towards 0, okay? They start off, your coefficient, your beta, basically your beta is something around like negative 280. Your beta up here is 400 something. And as lambda increases, these values tend to shrink, okay? This over here is the ratio between the norm, basically the total size of your beta vector, your vector of beta coefficients for using ridge regression versus OLS, okay? So in OLS, there's no penalty. Your betas can be as big as they want to be. And then with ridge regression, we say, we got to shrink these values. We don't want them as big as OLS is. And so on one end, if there's basically no penalty and the ridge regression coefficients are the same size, so basically the size of the ridge regression coefficients and the size of the OLS coefficients has a ratio of 1, these are basically the same coefficient estimates that we would get. And as we shrink this down, this numerator down to 0, we can see all the coefficients shrink. And so we can see up to some point, these we can see these two, the limit and rating coefficients, actually for a certain period of time end up taking on the same values and things like that. Okay. Again, why are we doing shrinkage in the first place? How does this help us? All right. How is this any good? Okay. These show the effect of shrinkage on the mean squared error for the test data set. Okay, so if we take we train our model on the training set, and we get coefficients, and we use those coefficients, we use that model to make predictions on the test set. Okay. This ends up being, this pink or this purple line ends up being the mean squared error. And so what we see when lambda is 0, okay, so when lambda is over on this side, the mean squared error is not as low as it can possibly be on the test set. And in fact, as we increase lambda, in this case, it actually goes down and then it climbs back up. What's going on is that as when lambda is close to 0, you have no bias. Okay, this black line represents bias. So when lambda is close to 0, or 0, you have no bias, because in OLS estimates are unbiased in the long run. Okay, that if you have your least squares estimates, they are centered around the true values. Okay, your least squares coefficient estimates are centered around the true values in the population, assuming your model is correct, or the form of your model is correct. But there's high variance in that if one person takes a random data set and someone else takes a random data set, your coefficient estimates could vary quite a bit from one to another. And so the mean squared error on the test set is kind of a combination of the bias and the variance, right? You add the bias and the variance together, and you're going to get the mean squared error. As you increase lambda, what happens is it reduces the variance. It reduces the variance, okay? But it comes at the expense of increasing the bias, okay? And again, this is a log scale. So the bias it climbs up quite a bit, but only when lambda gets pretty large in this case, and the variance gets reduced, but again, only at these kind of extreme values. And so what we end up getting is we end up improving our kind of the amount of error that we encounter with our test data set as at values where lambda is not 0. Okay, so at values where we decide to include a penalty term for having beta coefficients get too big, basically, that will reduce the mean squared error on our test data set. Right. And so our prediction, and again, it depends on the data set and the models you use. In some cases, your mean squared error will improve for values of lambda that aren't 0. Okay, and in some cases, maybe not. In some cases, the OLS model might still be the best. Okay, I don't know if that helps regarding why we want to do this. Maybe. So let me try to think of all right. Let's say you're given the job of predicting, predicting someone's weight based on other measurements of their body. Okay, and then so one person, so you collect someone's height and maybe their head circumference and their leg length, and I don't know, these other kind of other variables that may be highly correlated and stuff. Okay, and so let's say for your data set, in your particular data set, you find that height correlates most strongly with predicting someone's weight. Okay, but someone else, because of just kind of random chance, they end up choosing leg length. Okay, and says this one actually correlates stronger. Okay, now which one's actually better? Well, height and leg length are like super correlated with each other. So it's not unreasonable to imagine that either of those are probably okay, but maybe in your model, your coefficient for height is, I don't know, you're going to multiply it by 20, and the coefficient for leg length you multiply by 1, and then someone else for because of random data and random stuff, their coefficient for height is 2, and their coefficient for leg length is like 33 or something like that. Okay, so you have high variance in the coefficients that you get, and that's just something that happens when you have these kind of highly collinear predictors. Okay. When it comes to the test set, who's going to perform better? The one with using height or the one with leg length? And the answer is, well, I don't know. It's hard to know, right? Okay. Someone else, we could say, you know what? Don't just fit OLS, okay? But I'm going to give you a constraint, and then we're going to say that your coefficient for height isn't allowed to be bigger than 10, and your coefficient for leg length isn't allowed to be bigger than 10 or something. We just set some kind of arbitrary restrictions and say, all right, instead of doing 20 and 2 and 20 and 1 or 2 and 15 or something like that, so what this is going to force someone to do is develop a model where both kind of height and leg length end up having coefficients. Neither of them are going to be greater than 10, and so you might have a model where the coefficient for height is 8 and the coefficient for leg length is 9 or something. I'm just completely making this up, but does this kind of make sense? Yeah. All right, and so of these models, the one where they basically put all the weight on height, and then on the other kind of extreme, you have all the weight placed on leg length, and then something that's in between that says, all right, you know what, let's put do both height and leg length. Okay, which one do you think would perform best on the test set? And it's going to be the answer is maybe. Okay, again, depending on the test set, depending on our data, it might be the one where we kind of weight both of these things a little bit closer, rather than allowing one of the coefficients to be too extreme on one side or the other coefficient to be too extreme on the other side. So if you're unsure about which one is the correct one to use, it's kind of like an averaging out method. A little bit. Okay, and that's one of the effects. If you look at these coefficients, okay, in the beginning, using least squares regression only, we see the coefficient for limit is really high and the coefficient for rating is smaller. But as we increase lambda, it actually pushes up the rating to be around the same size as limit and reduces limit to be around the same size as rating here. Okay, but then as we increase our penalty for just having big coefficients, those both get pushed down to 0 as well. Okay, it doesn't always have this effect of kind of averaging. You can see, for student, it didn't actually ever get pushed up. It just kind of got pushed down. It's same thing with income and stuff. But these things can have that kind of effect. And basically, yeah, when you have predictors that display collinearity, we know that the coefficient estimates can vary dramatically, because just on the random data, it might appear that height lines up a little bit more closely with the predict response versus leg length or something. Yeah.
Isn't it that having high collinearity a model violation, one assumption? I think. Wouldn't you just want to get rid of?
Yeah, but which one do you get rid of?
Can't you do cross validation with each predictor, seeing which one performs better in cross validation?
Yeah. So there's different ways to kind of deal with it, and one is to just say, okay, if I've got these variables that are highly collinear, I'm going to do some kind of method and just throw one of those out. Okay, that's fine. but you're also kind of hoping that the one you threw out wasn't actually the good one, okay? And when you have things that are highly collinear, sometimes it's hard to kind of to know, did I throw out the good one because of just random variation in my data, or did I actually keep the right one, okay? And so so these shrinkage methods will say, well, you know what, don't just throw one out completely, okay? But we'll allow the model to fit, but we're also going to prevent any one of our coefficients from getting too big. So that's what ridge regression does, okay? Lasso does something similar, but it actually ends up having like a totally different effect. So with ridge regression, we took our betas and we squared them, okay? With Lasso, we take the absolute values. And you go, well, that sounds like a similar effect, okay? It turns negative values into positive values. Okay. But it actually ends up having a different effect. So when you square a value, big values get much bigger when you square them, okay? And then values close to 0 don't go to 0. They just, they get smaller, okay? So whereas Lasso, reducing something 5 points, going from 100 down to 95 is a reduction of 5 points. Going from 5 to 0 is a reduction of 5 points, okay? Whereas for ridge, where we have this beta squared, going from 100 down to 95, I don't know, it has a huge difference. I don't know what. Okay, let's just do a reduction of 10 because it's easier. 100 is 10,000, and then 90 squared is what, 8,100. So a reduction of 10 reduces it by like 1,900, okay, 1,900. Whereas going from 10 to 0 goes from 100 to 0. It's only a reduction of 0, okay? Whereas over here, going from 100 to 90 is a reduction of 10. Going from 10 to 0 is a reduction of 10. So ridge regression will prioritize shrinking the huge coefficients first, okay? And then once they're small, it doesn't really care, okay? So the huge ones get reduced first. With Lasso, everything kind of shrinks at the same rate, all right? It's going to shrink the 100 to the 90. It's going to shrink the 10 to the 0, 10 to 0, and 50 to 40. It's going to kind of shrink all of them at the same rate. We're going to apply, again, Lasso after standardizing the predictors. So with Lasso, we kind of push all of our, we end up shrinking our coefficients kind of down, okay, so as lambda increases. And so one thing you'll note is that as lambda goes, some of the coefficients get pushed exactly to 0, okay? Whereas with ridge regression, and again, this is still a log scale, you can see that they're a little bit more, their approach to 0 is a little bit more gradual. It looks, kind of asymptotic here. And again, this is lambda climbing at a exponential rate, okay? So they climb, shrinking to 0 is a lot more slower, okay? Whereas over here, as lambda increases, they get pushed exactly to 0, okay? And it looks like there's a curve here, but it's actually closer to straight line because, again, lambda here is on a log scale. Okay, so this, so these get pushed to 0 and exactly to 0, right? And so because the coefficients get pushed to 0 directly, this ends up having the effect of that we can use Lasso for variable selection. Okay, so Lasso will actually reduce some of the coefficients to exactly 0 and reduce the number of variables you even have in your model. If you look at kind of the thing that we're trying to minimize, okay? So we started off with OLS, we're just trying to minimize RSS. And over here, we're trying to minimize RSS plus this term. And over here, we're trying to minimize RSS plus this term. Okay. These are both kind of in the form of using a Lagrange multiplier to reduce a function subject to a constraint, right? So if you're doing, is that like multivariate calc or something? Okay, Math 32 something. Right, you're trying to reduce a function subject to a constraint. You basically add in this kind of constraint thing, right? You do a thing, minus 0 or something. So here we're basically saying, okay, we're trying to reduce RSS subject to this constraint, and we're trying to minimize RSS subject to this constraint. And so if you think about what is the constraint here, we're saying the constraint is that the sum of the beta terms squared is less than or equal to some constant. And over here we're saying the sum of the absolute values of beta is less than or equal to some constant. Okay? So imagine a model where we just have two predictors, beta 1 and beta 2. Okay? So if you take the constraint, the sum of the absolute values, in our case beta 1 plus beta 2 less than or equal to s, that's going to trace out basically a diamond, okay? And that, let's say beta 1 plus beta 2, the absolute value of beta 1 and beta 2 have to be less than, say, 10, okay? Let's say we want it to be less than 10, okay? So on one end, you'd have beta 1 is 10 and beta 2 is 0. This diamond would be, this corner would be beta 1 is 0 and beta 2 is 10. And along here, you would have like 1, 9, 2, 8, 3, 7, 5, 5, and 9, 1, and 10, 0. Okay. And then similarly, down here would be beta 1 is 0 and beta 2 is negative 10. And you would have 1, negative 9, 5, negative 5, and so on and so forth. And basically, that this shape here, this diamond, represents the constraint, the region of the constraint where beta 1 and beta 2 are less than s. Okay. Over here, if you have beta 1 and beta 2, this would be, with ridge regression, you're doing beta 1 squared plus beta 2 squared is less than or equal to some constant. Okay. And so if you have beta 1 squared and beta 2 squared, that's going to trace out a circle. Okay. And so that's what this is. So we have basically a subject to a constraint here. The constraint is that it has to kind of form a circle. Over here, the constraint is that these coefficients kind of trace out this diamond. Okay. This over here, these ellipses represent the contours of minimizing the residual sum of squares. Okay, we're trying, and this beta hat over here represents the OLS. This would be the value of beta 1 and beta 2 if we didn't have any kind of complexity penalty or shrinkage penalty. And we just said, okay, the value that's going to minimize residual sum of squares is going to be this quantity. So this is what OLS would end up picking. Okay, OLS would end up picking this. And we're saying, okay, we want to minimize the RSS subject to constraint. And so the ellipse that is kind of closest to this that ends up picking, that touches the this diamond is going to end up being here, okay? And because it's diamonds, it's going to generally favor where one of the coefficients is 0. So here we have beta 2 equal to 10 and beta 1 equal to 0 or something like that. Okay. Over here, this is the right here, where the ellipse touches the circle is the location where beta 1 and beta 2 are subject to the constraint and the values of beta 1 and beta 2 that minimize the RSS. And so here we have beta 1 close to but not equal to 0, and beta 2, some other value. So that's what this diagram represents. Okay, so you can think of it as minimizing RSS subject to a constraint using like a Lagrange multiplier. What does that constraint look like? For Lasso, the constraints look like these diamonds. For Ridge, the constraints look like a circle. Yeah, so basically as lambda gets bigger, the S gets smaller. Okay, so that the kind of the circle that we would trace out would get smaller. Whereas as lambda gets smaller, then kind of the radius of the circle would get bigger, and we can get something closer to the OLS. Same thing over here. Yeah.
How do we choose the range of lambda? Does it just start at 0 and go until the penalty is so harsh that our coefficients go to 0? Is that...
Yeah. So we have kind of tools. There's a few programs. There's packages, and you can read this here, the textbook where they do they work through it in the, I guess like there's a lab section in each chapter on how they do that. I was going to show kind of how to go about it with tidy models, and that's going to be kind of the next set of slides. But yeah, you can pick a whole bunch of different lambda values and see what effect it has. Okay, and this involves trying a bunch of stuff out. Okay. So I kind of did it in a little bit of a manual way, and I guess we could also perform a grid search, which maybe I should work on here. Okay, so here there's something called elastic net, and elastic net is like a hybrid of Lasso and ridge regression, and basically says, we're going to have this shrinkage penalty. What's the shrinkage penalty? The shrinkage penalty will have an absolute value component, and it will also have a squared component. Okay, so we're going to take our betas, the absolute values, and then we'll also take our betas and we'll square them. And how much do we want? Okay, there's a mixing parameter, alpha. And so if alpha is equal to 1, then it's just the absolute value component, and it's going to be the same as Lasso. When alpha is equal to 0, okay, this part goes away, and then it's just this side with alpha equal to 0, it's just going to be the beta squared, and then it will be equivalent to ridge. And you can have something in between, like alpha 0.5, where you're mixing the Lasso and the ridge components together, and you can try this out. Okay? And there's still kind of how much of a penalty to apply. You're still multiplying it by lambda. Let me give you your second view quiz answer. Today's second view quiz answer is the letter E. E as in elephant. E is your second view quiz answer. Okay, so we can do, we can look at tidy models, and we can use the engine GLMnet, okay, to fit these linear regression models with shrinkage factors, shrinkage penalties, okay? And so in tidy models, if you use GLMnet directly, it's going to ask for a lambda, it's going to ask for an alpha. In tidy models, it tries to pick terms that would be understandable even if you didn't read the documentation directly or something. Just because you could imagine some other paper, instead of using lambda, they use a different coefficient, phi, or something, right? So here, the argument penalty will define the lambda term, and that just tells you how much penalty should apply. And the argument mixture determines the alpha value, determining how much to mix between the two sides. Okay. In tidy models, the predict methods are designed to only make one prediction. Okay, and so that means as far as using a shrinkage thing, it can only make a prediction for a certain one penalty value. Okay, so if you're going to define a linear regression using GLMnet as your engine, you have to define what penalty value to use as far as where predictions go. Okay, what penalty value should be used when it comes to making predictions. But as far as fitting the model goes, GLM is actually going to fit with a bunch of variety of kind of penalty terms or lambda values. And so let me you know what? I think I need to clean up some of this. Okay, so, oops. Here, let me just kind of work through the screen here. So we're going to load up tidy models here. And we're going to take the Ames data set, okay, because we've been kind of working with that. To be honest, the Ames data set might not be the best data set to kind of illustrate some of the stuff here, just because, you know, OLS performs well when you have a bunch of observations, and in this case we do have a bunch of observations. So OLS, the coefficient estimates for OLS are fairly stable when you have a whole bunch of predictors. Okay, so, but again, you know, we kind of mutate the sale price, and so we'll do our initial split between training and testing sets. And we have, so here's a recipe that will normalize our predictors. And so for this recipe, I did not include any interaction terms, or I did not make a spline out of the latitude and longitude. Here I just say, okay, we're going to take, so if you look at the two, compare the two recipes. So this is the kind of recipe that we're familiar with so far. We take, we're going to try to predict sale price based on these other variables. And we're going to take ground living area and make it a log variable. And then we create another bucket for neighborhood. We take all of our categorical predictors and make them into dummy variables. And we added an interaction term, and we added a spline. We turned latitude and longitude into splines. Okay. Over here, I basically do a lot of the similar stuff, but I do these two things. I'm going to center and scale. Center and scale the all of our predictors. Okay, so this will normalize them. So you know, after we turn them into dummies and stuff, and we're going to kind of center and scale all of these things. And then I'm also going to kind of retain the means and standard deviations. I'm going to keep these terms from after centering and scaling them. So we're going to take this thing. I'm going to create we'll create our recipe. All right, and then we'll do the same thing over here. Other Ames recipe, we make a recipe there. Okay. In order to evaluate our model, we're going to do cross-validation. So I'm going to ask R to do v-fold cross-validation. I'm going to just do 10-fold cross-validation. And we're going to ask it to kind of save our predictions, save our workflow. And so this will be the folds that we develop here. Okay, so this kind of takes all of our data and it splits it. Okay, and we have 10 folds here. All right, so this is we're doing v-fold cross-validation, because what we want to do is we want to evaluate a bunch of models, and we're going to use cross-validation to kind of evaluate a bunch of models. And then at the end, we can run it against our test set. So again, initial split, training and test. And we're going to take our training data and we're going to do cross-validation. Okay, so here I did a whole bunch of these things, and probably maybe I should do a grid search later. Okay, but I didn't set it up here. But here I have kind of a bunch of these models that I want to fit. Okay, so one is we're going to just try linear regression. And so that will just be using set engine LM. Okay, here I'm going to fit a lasso model. And I just kind of arbitrarily chose penalty 0.001. The mixture value is set to 1. And a ridge is penalty 0.001 and the mixture value is set to 0. Okay, and then I'm just trying a whole bunch of these different kind of I'm going to just leave mixture set to 0.5, and I'm going to try changing different lambda values from 10 to the negative 5, 10 to the negative 4, 10 to the negative 3, 0.005, 0.01, and 0.02. And so we're going to set all of these things, and I'm going to create a list of basically all of these different models that I'm fitting. Right? Is that okay? So this is my list of the different models that I'm going to fit. And then I also have a list of the 2 recipes I'm going to fit. I've got my normed recipe where I take the predictors and I scale them. And then here the aims adds the what did it do? It added the interaction terms and then the latitude and the longitude. Okay, so we'll go ahead and we'll try running this. All right, and then we're going to, with all of these things, I'm going to create a workflow set. Okay, I'm going to try all of these models with the norm recipe. I'm going to try all of these models with the aims recipe. So we're going to create a workflow set. Our pre-processing, we've got 2 recipes in our pre-processing list. And I've got 1, 2, 3, 4, 5, 6, 7, 8, 9 models in my model list. And we're going to kind of do every kind of combination. So this will do 18 different kind of recipe model combinations using tidy models. So we're going to run this workflow set here. Okay. So this, we have it lists them off here. Norm LM, norm lasso, norm ridge. Okay. Here, I can say, then take, we're going to run the workflow map. And we're going to run the function fit the resamples. We're going to take all of the models in our workflow set, and for each model, we're going to run fit resamples, and we're going to fit it onto the aims. Okay, and we'll keep all of our predictions. All right. So I'm going to go ahead and do this. Now this takes a little while because it's fitting. Uh-oh. Oh, dear. That's not going to work. Okay. Okay, I have to do library glmnet. That was, oh, what? Okay. Weird. Sorry, let me back up. Library glmnet, we'll run that recipe, we'll run this recipe, create our 10-fold cross-validation, create a bunch of different models here, create a workflow set. Okay, now Now we'll go ahead and run this. Okay, so this will take a little while because it's got 18 of these things to do. 2 of 8, so norm, linear model, norm lasso, norm, ridge, norm, GLM, 10 to the negative 5, 10 to the negative 4. So it'll take a little while. Okay, it's running. Maybe I'll post the script as well, just so you don't have to copy and paste from my slides. Okay, so it's doing the normalized recipe, and then now it's going to do the same thing, but with the Ames recipe. Okay, I think it's done. Okay, so that finished. All right, and then let's take a look at our metrics here. So it gives us the RMSE for all of our different things. Let me go ahead and scroll, and so we have these kinds of terms here: 0.095, 0.09, 0.078, and we can see all of these things. So these one use the normalized ones, the other ones use the Ames. Okay, so I can click the auto plot here to ask, okay, what does this look like? Preprocessor recipe. I need a way to label these things. Okay. Well, we see there's a difference, and we got some of these things down here. Okay, so what you can do is you can take all of these models, and you can say, you know what, I want to rank these based on the RMSE. So we'll rank them. Okay, and so when I run that, the best performing model here was the linear model on Ames, and then the second best performing model was the using the Ames recipe, so where we included the interaction terms, and we didn't normalize them. Maybe I should have modified my recipe. I wonder, okay, well, we can try it again. So here, after we include the interaction terms and the spline fits, the one with the smallest amount of penalty is the second best performing one. And then as we increase the penalty, it seems like our RMSE gets a little bit bigger and bigger, okay? Lasso outperforms the ridge regression, which outperforms having even larger amounts of penalty. So the lasso and the ridge all have penalties of 0.001, and these, and it seems like GLM with penalty 0.001 outperforms Lasso, the mixture. So again, if we recall these different things, this mixture where the penalty is 0.001 and the mixture is 0.5 outperforms Lasso with the penalty of 0.001 and Ridge where the penalty is 0.001. But these two models where we have the mixture and the penalty is even smaller, outperform. As we increase the lambda term, it seems like our performance is going down. Okay, and in fact, the one where we had no penalty term seems to be the one that performs the best. So again, perhaps this data set just is not a good example where using these shrinkage terms results in the best. Okay, but let's just kind of compare these two. We've got Ames linear model versus Ames with 10 to the negative 5 as a penalty. And so we'll go ahead and try test its performance on the test data set. Okay, so I'm going to take my workflow or create a new workflow. We're going to take our linear model, add the recipe. Okay, because we're not fitting the resamples anymore. We're going to just take this model that we designed. We're going to fit it on the training data set. Oops. And then using those fitted results, we will make predictions on the test data set. And here we'll measure the RMSE on the test data set. Okay, are we able to read this tidy model stuff? So here we're going to take the just the linear model with the Ames recipe to create a workflow. We're going to fit it to the test data set where we're going to compare the sale price. So maybe here we can see, okay, these are the actual sale prices, and we're going to compare it to our predicted sale prices. We're going to ask what's the RMSE here. And we get 0.0736. Okay, and then we'll try it with this model where we have the smallest amount of penalty. We'll fit it to our data on the training set. We'll make predictions on the test set. We can see, the values, how do they compare? And so, yeah, indeed, the regular linear model, 0.07362, has a little bit of a lower RMSE than using our shrinkage terms. Okay, so again, perhaps this data set, maybe not the most illustrative one. There is kind of a lot on tiny models. What is this? There's quite a bit that you can read in the documentation. If you don't use a workflow, and if you just create a model directly, so there's a function called Multipredict, which doesn't work with a workflow, but it works with kind of a model directly. You can use it to create predictions for different kind of penalty values. So you can kind of say multi-predict, and you can give it a vector for penalties. And you can go 0, 0.01, 0.02, so on and so forth. And you can decide on that. GLMNet itself also, and perhaps I will have to I'll post some notes from a different class, 102B. If you want to use some of the functions built into GLMNet, there is a tool that tries to estimate what is the best value of lambda to use. Okay, and there's kind of some internal cross-validation stuff that it can use, and it can there's this value called lambda.1se after you do CV fit, and so this is a possibility where the package glmnet tries to estimate what value of lambda or penalty you should use. The unfortunate thing is that this is where you realize where tidy models is nice, is that in order to use glmnet, it requires you to reformat your data, which is annoying. Okay, so in tidy models, you use a recipe, and you put that recipe into a workflow, and then it fits the model. If you want to use glmnet directly, you have to get all of your values into an X matrix and all of your response values into a vector Y if you want to use glmnet directly. And that can be a pain because that requires you to kind of manually run your recipe yourself. So I don't know if this is a recommended tool or strategy to employ, but you know, all of these things that tidy models interacts with, you can go to the package directly, and some of those packages will have additional features that perhaps have not been implemented into tidy models directly, right? So that's one aspect. Although, you know what? Let me think about it. There's extract model fit, right? I wonder, maybe. No. Okay, yeah. So there's a function cv.glmnet that will try to do cross-validation to decide what value of lambda to use. Maybe I'll just post these notes as kind of a supplement. Not that you're required. Okay. All right. So anyway, that's using shrinkage and regularization methods, and again, tidy models allows you to fit a bunch of these things. In we can also run a grid search, and I guess I'll have to incorporate these things into another set of lecture notes here. Okay, this is actually this is all I have prepared for today as far as fitting models, and you know, we fit using tidy models. We fit a whole bunch of these different models here. And I suppose if I wanted to, I could add another recipe, and we could sit through the process. And I won't make you guys endure that, but I could take this recipe and I could add this step of centering all the predictors and scaling them. So I can do Ames recipe scaled or something, and run that as well. And we would have to add this to the list of pre-processing steps. We'll call this Ames scale, and we'll run that. Okay, but I won't do it because it'll take a while. But that's kind of a nice thing that, you know, now instead of 18, we're going to have 27 of these things to fit. And maybe I will just remove this one because this one actually performed the least best of the other models. But you can, that is kind of a nice thing that you can set up these workflow sets to try out a whole bunch of these different models. Okay. Let me give you a last view quiz answer. Last view quiz answer is A. A as in apple. A as in apple is the last view quiz answer for today. Okay, we'll end here. I'll continue to work on setting up homework 3, and I'll get you the rubric for the report and what's expected, and then I'll send out a poll to see if students would rather the final exam or would rather do a classification set. Okay, all right, have a good day, and we'll see you on Friday.
What were 5